All right, here we are. We've got this particular problem. It is kind of like a time trial problem. It really needs you really need to know all the reactions. But not only do you need to know how to predict the products of the reactions, or in some cases, even the reagents that lead to a certain product, you have to know the regioselective and stereoselective outcomes of these reactions as well. So you have to be able to write all that information down correctly. So let's get started. The first one is the addition of HBr. In the regular addition of HBr, we would be adding HBr in a Markovnikov fashion. So the Br would add to the more substituted side, but this is in the presence of peroxide. It's a radical reaction and we haven't seen the mechanism yet. So, but what we do know is we know that the Br adds to the more substitute, it's the least substituted side. It's actually anti-Markovnikov. Now, both steps actually happen separately and they're radical steps. So they both lead to both possible stereochemistries in the product. So that's what that squiggly line indicates. It indicates that the CH3 could go either direction, and then in the next step, the Br could go either direction. So it's not syn, it's not anti, it could be either one, just depending on what happened. So there would really be 4 possibilities because you'd have all combinations possible. Now, the thing is you don't know the mechanisms of this reaction at this point. So generally what we would just expect a student to do is that, showing specifically the regioselective outcome. Okay, now the next one you would need to know, it's H2 and platinum catalyst. I'm going to fully reduce the double bond. I'm going to add H2 across the double bond, but I'm going to add that in a syn fashion. So that means that I have to show my CH3 and my ethyl group pointing in the same direction. And also I could have created the enantiomer. Now, remember, when I write En, I really mean the enantiomer with respect to only the stereochemistry of the double across the double bond, what's formed at the operative double bond. If there's other stereochemical or other stereocenters in the molecule, then really the relationship is that they're diastereomers. Okay, so what's next? So in the next one, I want to show you that I'm forming a diol, and there are 2 reactions that form diols, 3 reactions that form diols, but only 2 of them form syn diols. One of them would be with osmium tetroxide. The other one would be with potassium permanganate. And so we just want to fill in the reagents there. Okay, the next one is ozonolysis. So remember, the way that I show students to think about ozonolysis is to think about it in terms of splitting the double bond. The double bond's going to split, but that's the only thing that's happened. The functional structural motif of the double bond stays in place. It's just that the double bond splits and each side moves away from each other. And in place of at the end of the double bonds, instead of just being nothing, I'm going to put oxygens. So I'm going to make a carbonyl group there. So what do I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, I think. Let's see, I got a double bond here. I think I need another carbon. Okay, now I can put my double bond here. Let's double check. I have 1, 2, 3, 4, 5, 6 carbons in between the 2 carbonyl groups. Let's see if I got that right. 1, 2, 3, 4, 5. Okay, 6. I got that right. Okay, so the next one is a situation where I have an alcohol, but it seems to have added at the least substituted position. So it's an anti-Markovnikov addition of an alcohol. And it's also a syn addition. Take a look here. The hydrogen does get added across the double bond, and it's pointing the same direction as the alcohol. So the only reaction that forms an alcohol an anti-Markovnikov position, and it also happens to be syn addition, is hydroboration oxidation. And so that's the answer for this one. It's BH3. I can always write BH4. What's my deal? BH3 and THF with sodium hydroxide and hydrogen peroxide. And so we're good there. Okay.